Okay, welcome back, everyone. We are now into entropy. This is chapter 2.3, and we are now about to start real live statistical mechanics. We're going to think about how to apply these ideas of the microcanonical ensemble and microstates and being able to put it together to determine a property that we didn't really have before. Okay, so in section 1.2, I skipped it. It attempts to explain entropy based upon observations and experiments. We tried to do this for you in general chemistry as well. We tried to define entropy as a measure of the disorder of the sample, a very cerebral, vague sort of description. But now that we understand a microcanonical ensemble, we can create a real definition of entropy. And entropy is really a key driving force for all reactions, and it's a parameter that ties all of science together. Your textbook calls this the most important parameter in science. And entropy is so important that Boltzmann, who defined entropy, has his equation for entropy engraved on his tombstone. I would love to have an equation engraved on my tombstone, but I don't think that's going to happen. But for Boltzmann, it did. And that is because entropy defines all of chemistry and therefore most of biology and science in general. So the Boltzmann entropy is that S, or entropy, S is entropy, is defined to be equal to Kb, which is the Boltzmann's constant, times the natural log of omega. And remember that omega is the number of microstates in the system. And we talked about this in the last video. So in reality, entropy is nothing more than a count of the number of microstates, because we're not doing anything. We're taking the natural log, which just gives us another number of microstates, and we're multiplying it by a constant. And so we're not really there's no other changing number in here. There's no derivation for this. It's just that entropy is basically proportional to the number of microstates in a system. So entropy is nothing more than a number, a count. So some things about the number of microstates, this omega value. The number of microstates in a system is finite. So it's a countable number. But it is a very large number. It is not equal to infinity. Okay, so it's a number that we can actually count. So to give you a sense of what we mean, the entropy of 1 mole of helium gas under typical lab conditions is measured at 126 joules per Kelvin per mole, which are the units for entropy. If we use this and we plug it back into S equals Kb natural log of omega, and we solve for omega, we get that omega equals 1 times 10 to the 95 microstates. So a very large number, but not infinity. Okay, so, this raises the question, why not just work with microstates? If entropy is a count of microstates, why do we not do our math with just omega? Well, it turns out that the math with omega gets really tricky. So if I have two samples, I have sample A and sample B, and I'm going to mix them together. Nothing more than I am going to take my water and I am going to add ethanol. I'm going to add vodka. I am going to dilute my vodka or gin or solvent for the lab. Sample A has an omega number of microstates, my water. Sample B, my ethanol, has an omega number of microstates. So the total number of microstates in A and B is equal to the multiplication of the microstates of A times the microstates of B. Well, because these are large numbers, if we take the natural log, our numbers get more manageable. So if we take the natural log of the omegas, then we find, and we do our log math, we find that the natural log of omega A plus the natural log of omega B, or that the natural log of omega A times omega B is equal to the natural log of omega B A plus the natural log of omega B. Multiply all of this by K, and we get this definition of entropy. And so really working with entropy is really the same thing as working with microstates. It's just we get to avoid the super large numbers. Okay, so the Boltzmann entropy, this is our S equals K log omega. It is a beautiful equation. So simple, but it's rarely convenient to use. It's really hard to count and get a number for omega. So if we need to look at a system that is changing, for example, a reaction, then determining this value for omega becomes very difficult. Remember that suddenly the microcanonical ensemble approximation really isn't valid anymore. So to deal with this, Gibbs, yes, Gibbs free energy, Gibbs, the same person, defined the number of microstates in terms of probabilities instead of counts. And this created a term known as the Gibbs entropy. And this is a much more usable definition of entropy than the Boltzmann's entropy. So the Gibbs entropy is that entropy is equal to N, the number of particles in the system, and these are identical particles, times the Boltzmann's constant, times the sum of the probabilities of each quantum state existing. And so this P sub I is the probability of a microstate. And we're going to sum from I equals 1 up to K. Why we keep using K, I don't know. And K is the number of quantum states, which you can think of as microstates, available. Okay, now the Gibbs entropy is not like the Boltzmann's entropy, where the Boltzmann's entropy is a defined term. If you look back, we wrote it as S is defined to be K log omega. that is a definition. I guess I shouldn't use a underline for my triple equal sign. That is a definition. This indicates that this is a derivation. And that means that we can mathematically transition between the Boltzmann's entropy and the Gibbs entropy. That there is a mathematical connection here. And your book works through the steps connecting these dots. I'm not going to do it on these slides, but you are welcome to read about it in your textbook. Understanding how we get between these is not something that I am looking to test at this point in the semester. But I will expect you to be able to use both the Boltzmann's entropy and the Gibbs entropy. But at this point, what you should recognize is that these are both measures of the same entropy. They're just different ways of defining what a microstate is. Okay, so your now try this is that a system includes two particles occupying 4 microstates. Remember, that's our 2 particles, 4 possible spots. All of these microstates are equally probable for the particles to occupy. And with this, I want you to calculate the Boltzmann's entropy and the Gibbs entropy for this system. With this, you have all of the information that you need to complete homework 1. Over the next couple of days, I'm going to start getting you the videos to get you started on homework 2. Okay.